Okay, good afternoon. We were looking at transformers in the last class, and what I had done was to give you the basic principle of operation and also the derivation with regard to the voltage output of a transformer, how the primary voltage and secondary voltage can be derived. So to reiterate the working of the transformer, what we said was that a transformer going to have a ferromagnetic material made up of, a core made up of ferromagnetic material. So in the around the core, so if I say that this is the core of the transformer, which I'm just showing as a two-dimensional figure, but it is actually a three-dimensional thing. So I'm going to have this as the core of the transformer. I'm going to have the primary winding wound like this, which is going to be excited with an AC voltage. So I'm going to apply an AC voltage V1 here. And on the secondary side, I'm going to have the winding, which is actually having a different number of turns probably. So let us say this is the number of turns here is N2. This is going to be N1. And we are going to have a current flowing through the primary, because of which a flux will be set up in the core. So the flux, I can show it somewhat like this. So it is going to confine itself as much as possible to the core, because the core is made up of ferromagnetic material whose reluctance is really, really small as compared to surrounding air. So we are going to have the secondary winding completely linking with the common flux that is existing between the primary and secondary, which is also the mutual flux, which is existing actually in the core. And because of that, I'm going to have an induced EMF E2 here, but simultaneously I'm going to have an induced EMF E1 here, which will almost balance with that of V1. If we neglect the resistance and any leakage that happens in the flux, I can say V1 should be approximately equal to E1 if resistance of primary winding and the leakage flux are neglected. If both these are neglected, we are going to say V1 and E1 are almost equal to each other. The same way, I will have essentially an E2 induced on the secondary side, and there is hardly any current flowing on the secondary side if I don't connect any load. This is on open circuit. So this is no load, or I can say it is on open circuit. Secondary is on open circuit. So in which case, I am going to have a voltage at the terminal, which is also incidentally equal to E2 because there is no drop. So I'm going to have V2, which is the terminal voltage of the secondary. That will be equal to E2. That is going to be equal to E2. Okay. So V2 and E2 are exactly going to be equal to each other, especially when you are going to have no load connected across the secondary. Okay. And we also said that because the flux is to both, d phi by dt is going to be the voltage induced per turn of the primary or secondary, either way, of the primary or secondary winding. So from which we said that we are going to write E2 will be equal to N2 multiplied by d phi by dt, and similarly E1 is going to be equal to N1 multiplied by d phi by dt. So we are going to say that E1 by E2, which is also incidentally approximately equal to V1 by V2, V1 being the applied voltage. That is going to be N1 divided by N2. So I should be able to write this as N1 d phi by dt divided by N2 d phi by dt. This is what we said as the basic working of the transformer. And we also said that if I assume a sinusoidal excitation is given, so this voltage V1 is sinusoidal. If I'm going to give a sinusoidal voltage, then in all probability, the current that is being drawn will also be sinusoidal. So the flux will be fairly sinusoidal. So I'm going to have essentially phi equal to some phi m sine omega t, from which we can write this as phi m multiplied by sine 2 pi f t. Right. So I can write this as d phi divided by dt, which is voltage per turn. For one turn, I'm going to have this as phi m multiplied by 2 pi f multiplied by cos of omega t. Right? So this will be the peak voltage. So in which case, that is, this magnitude is going to be the peak value of the voltage. So if I want RMS value of this voltage, I have to divide this by root 2. So which means I'm going to write root 2 multiplied by pi multiplied by f multiplied by phi m. So this root 2 pi is going to work out to 4.44. So I'm going to have 4.44 multiplied by f multiplied by phi m as the voltage RMS value per turn. So this is going to be per turn. So that is the reason why we wrote E1 is 4.44 f phi m multiplied by N1 and E2 equal to 4.44 f phi m multiplied by N2. Right? And we also said that if we are connecting a load on the transformer secondary side. So let's say this is my core of the transformer. And I'm going to have the primary winding connected here, wound around the one of the limbs, and secondary winding here. And I am trying to connect a load across this. So I'm going to show a load. I don't know whether it is going to be resistive, whether it is going to be inductive. I don't know whether it is going to be capacitive. So I'm going to say this is the load, some impedance Z that is connected here. And this is the voltage what I'm applying here. Let me show that as V1. What I'm applying here is V1. So V1 is applied here. Okay. So when I initially connect the voltage source without really having any load, I would have had the flux established here, which would have been somewhat like this. So the flux is established in the core, which is actually shown like this. So this is going to be the flux. Okay. So I'm going to have the flux established, because of which there is a voltage induced, which is E2. I may call this as E2 or V2. So this is the voltage induced. Now, when I connect the load, this is going to have a current flowing through this. Once a current flows through this, that will not keep quiet. That will also definitely create a flux. And by Lenz's law, so as per when you look at transformer action, as per Lenz's law, you are going to have the flux, what is here, that is going to oppose the original flux. So I should draw the flux induced because of this secondary side current that is going to be exactly in the opposite direction to that of the original flux. So If this persists, the original flux will be killed. If the original flux is even decreasing slightly, then immediately I'm going to have d phi by dt decreasing. This is going to decrease. Because this decreases, there will be a difference between V1 and E1. Even if the difference is really small, V1 minus E1 divided by whatever is the impedance of this coil or resistance of the coil, the resistance of the coil is going to be really low, because of which we are going to have a high current drawn by the primary. So a high current will be drawn by the primary from the voltage source. So when you have a high current drawn by the primary, obviously you are going to have N1 multiplied by that I1. If I may call this as I1, N1 multiplied by I1 will be the MMF, new value of MMF, magnetomotive force. So that is going to actually increase the flux quantity until it bounces back to the original value. And once it bounces back to the original value, everything will be exactly like what was originally the case with the no load condition, when there was no load at all. So you are going to have E2 again and E1 again in the primary and E2 again in the secondary. And still the load current will be flowing through this. If I may call this current as I2, the amount of increase in the current in the primary side will be exactly same as that of the MMF that caused the reduction in the flux. The MMF that caused the reduction in the flux was I2N2. So we should have I1N1, what has been the increase in the MMF provided by the primary, that should be equal to I2N2, so that they nullify with each other and the original flux is undisturbed. It will not be disturbed at all. So generally you are going to have this ampere turn balance always followed in a transformer. Ampere turn balance between the primary and secondary will always be followed in a transformer, such that whatever is the additional current drawn by the load on the secondary side will be compensated for by the primary side by drawing additional current, so that you are able to come back to, the core is able to come back to the original flux condition no matter what. Otherwise, the transformer action itself will cease to exist. It will not, a transformer action will not exist anymore. So this is essentially giving us clearly the relationship equal to I2 divided by I1. That is going to be equal to N1 divided by N2. And we had already said this is equal to V1 by V2. From which roughly I can say V1 I1, the volt ampere of the primary, will be approximately equal to V2 I2. Actually, in an ideal transformer, V1 I1 and V2 I2 should be exactly equal to each other. And generally, the efficiency of a transformer will be as high as 97% or 98%. There is really not much of loss that will take place in the transformer. So for all practical purposes, it's okay to say V1 I1 equal to V2 I2 unless you are calculating the efficiency very accurately. Okay. So until now, whatever I have said is just recalling whatever we did in the last class. So as an example, let me try to just give you a simple numerical example to know the kind of flux values that we are going to have in a transformer. So let me take a single phase 2.2 kVA, 220 volts divided by 110 volts transformer. So it's a step down transformer. 110 volts transformer has 85 turns in the primary. Calculate the peak value of flux in the core, comma, number of turns in the secondary, primary and secondary current ratings, if the transformer frequency, the transformer operating frequency is 50 Hertz. Okay. So let us try to take a look at this. We should use the voltage equation of the transformer, what we had used. Please remember what did we derive? We basically derived E1 equal to 4.44 F phi M multiplied by number of turns. Right? The same way we said E2 equal to 4.44 F phi M multiplied by N2. Okay. So in which case we can directly use this equation and we can say 220 volts is the primary voltage if I assume that E1 and V1 are equal to each other. What we are applying is 220 volts. So if V1 and E1 are approximately equal to each other, 220 volts will be equal to 4.44 multiplied by 50 multiplied by phi M multiplied by the number of turns, which is 85. From which you should be able to calculate what is phi M. So phi M value comes out to be 0.0124 Weber. This is going to be the peak value of flux, what is circulated or what is the mutual flux that is linking both the primary and secondary winding. That is going to be this. Okay. Now to calculate the number of turns, which equation will, so E1 by E2 will be equal to N1 by N2, which is actually 220 divided by 110. Right? And N1 is given to be 85. So you are going to have this as half of that, which will be 42.5 turns. So this will be the secondary turns. You can't have half a turn. So you will normally use closest, integer. You will round it off to higher integer. So that is 43. So approximately 43 turns will be needed on the secondary side. So it will increase the voltage slightly. Yes, it will definitely increase the voltage slightly. But 43 turns will be the number of turns that will be needed in the secondary side. How will we calculate the current rating? The volt ampere of the transformer is given to be 2200, 2.2 kVA. So that is 2200. So we can say ampere or current, rated current. I can write rated current of the primary. That is I1. If I want to calculate, I should say 2200 divided by V1. And V1 is given to be 220 volts. So we are going to get this as 10 ampere. Very clearly the secondary side current. So if I try to calculate rated current of the secondary, I will have that 2 times this value because the voltage is halved. So I'm going to have 2200 divided by 110, which is going to be 20 ampere. Right? So this is going to be I2 value. Please note that the power or the volt ampere is the same if I look at it from the primary side or the secondary side. It's not going to be very different. So if the voltage is stepped up, current is going to be stepped down and vice versa. Okay, so that's what is being done in this particular case. Okay, so let us try to now look at the actual transformer. Until now, we had only looked at V1 and V2 are exactly equal to each other if the number of turns are same. So which means we are neglecting any resistance drop, any other leakage in the flux, everything we are neglecting. So let us first of all look at transformer on no load, and then we will look at transformer on load, both. So when you look at the transformer on no load, that means I am not going to connect any load on the secondary side. So let me again draw this. This is the core of the transformer. And I'm going to have the primary winding from here. And I have connected a voltage source, which is V1. Okay. And I am looking at the secondary winding being wound around this. And I have not connected any load here. And if I try to measure the voltage, it is going to be E2 or V2. This is going to be the voltage. Okay. Now, as I mentioned earlier, these two portions are generally known as yoke of the transformer, and these two vertical limbs or vertical portions are generally known as the limbs of the transformer around which you are winding the winding. So these are essentially limbs of the transformer. Okay. Now, when I am actually connecting a voltage source here, because it's a copper winding, I am definitely going to have a current flowing through this. But I don't have any load connected here. So the secondary winding current I2 is equal to 0. So whatever is the current that is drawn by the transformer is mainly for establishing the flux. It doesn't have any other purpose other than establishing the flux. And if I look at the reluctance of this core, because it's a ferromagnetic material, I'm going to have the reluctance of the core is very, very small. This is going to be very minimum. It will not be a large value at all. So when I talk about MMF divided by reluctance equal to flux, and what I need as flux is a finite quantity to induce a particular value of EMF, which is decided by this equation. Phi m is going to be whatever is the voltage, which is V1 or V2 divided by 4.44 frequency and number of turns. This is going to be deciding what is the kind of flux I need to establish in the core so that this amount of voltage is induced. So the flux is a finite quantity. The reluctance is really, really small. So we are going to have MMF also to be small. The required MMF is going to be really, really small when I'm talking about a transformer which is having ferromagnetic material as the core material. The required MMF is going to be really small, which means the current, what is required under no load condition, just to establish the flux. I call this current as I0 or no load current. I'm going to call this as no load current of the transformer. that is going to be really small because of this reason. Okay. So that current mainly establishes the flux in the core. So if I try to draw the phasor diagram for the transformer under no load condition, the common quantity between the primary and secondary is the flux. So I'm going to draw this as the common quantity, which is also the flux. So let me call this as the flux. Okay. Now I'm going to have a magnetizing current or I naught drawn by the transformer. The magnetizing current is actually the current which is needed for establishing the flux. So let me call that as the magnetizing current. I'm going to show this as IM, which is the magnetizing current. Okay. This current definitely will be inductive, because every time you talk about flux, reluctance and everything, it is all about inductive. The current is being inductive. Because it is inductive current, it will lag the voltage by 90 degrees. It will lag behind the voltage by 90 degrees. So if I show the voltage, I should show the voltage exactly like this. This is what is my applied voltage V1. And the magnetizing current will lag behind by 90 degrees. So this is going to be 90 degrees. Okay. But I have not mentioned this as magnetizing current. I have mentioned this as I naught. That is because if I am actually looking at what is the kind of, real component of current, whether it will draw any real component of current, because this is inductive or reactive component of current. I can say this is reactive component. But after all, I'm establishing this flux in the core. The core is made up of ferromagnetic material, because of which it will have a property of hysteresis. So if I try to look at what is the kind of B versus H relationship this core will have, it will essentially have a relationship like what we studied in the magnetic circuit. So we are going to have something like this going on in the core in terms of establishing the flux or flux density with respect to the current or magnetic field intensity that I'm applying in the primary winding. So I will have hysteresis loss incurred by this core material. So I am going to have something called core loss in this transformer. The core loss actually will consist of hysteresis loss and another component called eddy current loss, which I made a passing mention earlier. So let me probably write this clearly, that I am going to have two components of losses which are known as core loss, that is happening in the ferromagnetic core, that will consist of two components. One is hysteresis loss and the other component is going to be eddy current loss. So there will be two components of losses of the transformer, and these losses are real power losses. You are going to see this actually manifested in the form of heat energy that is dissipated through the core material. So when the transformer works, the core will actually get heated up. That is because of this core losses. So whenever you are talking about real power or heat dissipation that is taking place, that cannot happen unless there is some real component of current. So this core loss is represented as I square R loss. It is represented. It is not in actual practice. The core is not going to draw any current. It is actually represented. The core loss is represented by a real component of current, which we call that as core loss component of current, IC. So this core loss component of current is a fictitious current that is actually going to that will be representing the real power loss that is taking place in the core in the form of hysteresis and eddy current losses. So when I add these two currents together, I'm going to say totally what I am looking at is I naught. So I naught will basically consist of a very, very small real component of current and a pretty largish within this I naught. If I see, a good fraction will be Im and a smaller fraction will be Ic. So these two currents put together vectorially, when I add, I am going to get that as the total no load current. So if I try to look at what is the no load power factor, this will be the no load power factor. So cos phi naught, if I try to write, that is going to be essentially the no load power factor, and that no load power factor is going to be really, really poor for a transformer, because the core loss in a transformer will be as minimized as possible by at least reducing the eddy current losses. Hysteresis loss essentially depends upon the core material property. I don't have any control over it. I can have a control only based on the frequency. If I have a lower frequency, the hysteresis loss will be lower. If I have a higher frequency, hysteresis loss will be higher. Right? Because we said that this area under this loop represents what is the energy loss per cycle. So if I have more number of cycles per second, I'm going to have a higher wattage loss. Okay, so I will have essentially this as my magnetizing current and this as the core loss component of current, and the summation of these two is going to give me what is known as the no load current. Now if I try to look at what is the kind of E1 and E2 I have, I'm going to have E1 and E2 I'm showing like this, because I generally write N d phi by dt equal to minus E. That's what I'm going to write. So I can write these two as E1 and E2. This is the induced EMF that I'm going to see depending upon what is the kind of turns ratio I have. So the no load phasor diagram of the transformer is basically represented by the flux which is common to both primary and secondary, then a magnetizing current which is almost in phase with the flux because that is the root cause for flux production, and I'm going to have a small current which is the core loss component of current, and when I add these two I'm going to get the no load current. So this is the no load current of the transformer. Okay, so here I should be able to say that cos of phi naught will be equal to, I should have whatever is the IC value divided by I naught, right? And similarly, sine of phi naught, I should be able to write that as whatever is the magnetizing current divided by I naught. So this is the no load power factor. This is going to be the no load power factor of the transformer. Okay. Any questions on this? Any questions? Do you understand the no load condition of the transformer? Any questions? So if you have kind of understood this, let us first of all try to look at what is eddy current loss and how do we reduce it by laminating the core of the transformer. So let's try to look at what is eddy current loss. So eddy current loss generally is because of induced EMF in the core material. And that too, this induced EMF will also circulate a current in the core material. This is because the core itself is not an insulator. It is a conductor. So it is going to have a complete thoroughfare for the current. It will go and circulate in all sorts of direction. So that is going to cause I square R losses in the core. So this is really due to some current circulating in the core, and that is going to cause I square R losses in the core. And if we can minimize it, that will be good. So how do we really minimize it? If I say that this is going to be the core and I'm going to draw the three-dimensional core. So let us say this is the kind of core I am talking about. And I'm going to have three-dimensional core. So let me show it like this. So I'm going to have this as the solid portion of the core. And I would be able to see the inner portion somewhat like this. Right? This is how the core will be. Okay. Now, what I would see normally is the flux is going to be established somewhat like this. This is how the flux will be established. So the flux actually is established along this plane, which is the front portion of the transformer. Now the current induced will be perpendicular to this. So the current induced will be actually going along this. This is going to be essentially perpendicular to the flux's plane. So this is how the current induced will be within the core. So this is the current within the core. This is what is going to happen. Okay. So if I have a solid core, I would see that, let me draw only this portion, whatever I have got here. Let me first of all try to show it here. So this is the portion through which I'm going to have the current, eddy current circulating in all sorts of different directions. So I can have the eddy current circulating in all sorts of different directions, because if it is a solid core, I'm going to have the current flowing in whatever direction it feels like flowing. It's not a problem at all. Rather than that, if I try to make this as one piece, which is having the core exactly this way, and it is a thin plate, and behind that I'm going to put another thin plate like this. So I'm going to have another thin plate, and I'm going to put a third thin plate like this. So I'm going to have one after another, many thin plates are put up, which means if I try to look at this side again, if I try to look at this particular side, how this will look like, I will have actually this as the side view with many laminations one after another stuck together. So I'm going to have many of them stuck together like this. So if I look at this plate, it will have a flux like this. Behind this, it will have again a flux. The third plate will also have a flux. So each of them will have flux, and each of them will have induced currents which are perpendicular to the flux direction, but it has to circulate, the induced current has to circulate only within this thin sheet, nothing more than that. So it has to circulate like this. It has to simply circulate within this thin sheet. So if you look at each, if there are, let us say, 10 laminations instead of one solid core, if this particular core is made up of 10 laminations or 10 stampings, then what is going to happen is, if the total flux had been phi Weber, then flux per lamination will be phi divided by 10. This is going to be the flux that is available in each lamination. Okay, so obviously I'm going to have the voltage is normally proportional to flux. So voltage per lamination now will actually be reduced by a factor of 1/10 of the original voltage. That is one thing. And second thing is, I am going to have essentially I square multiplied by the resistance offered by the lamination or resistance of the core. This is going to be the I square R losses or eddy current loss of the core. Now, because I'm having the voltage to be 1/10, the current will also be 1/10. So originally, if the current had been I, if the current circulating in the entire core, had been I, now I'm going to have the current in every lamination has to be I by 10, because I'm talking about, first of all, the voltage as though the voltage has decreased by 1 by 10 factor. That is the reason why I'm going to have the current to be 1/10, provided the resistance of the core is the same. But the resistance of the core is also not going to be the same, because I'm not allowing a thoroughfare for the current. I have kind of insulated one lamination from the next lamination. Right? So that is the reason why the current will not be able to circulate as as easily as it was circulating earlier. So the resistance will be roughly increased by a factor of 10. So resistance will be increased because the cross-sectional area through which the current is flowing, that is also kind of decrease. So you're going to see that the resistance will be increased by a factor of 10. So 10-fold it is going to increase. So you're going to see that the current in every lamination now has decreased rather by a factor of 10. I divided by 10 because of the voltage reduction, and another 10 factor comes because of increase in the resistance. So this is due to increase in R, and this is due to the reduction in E. So both of these are going to play a very vital role in reducing the current through the core. Now, if I try to look at what is I square R loss per lamination, that is going to be now 1 by 100 times whole square multiplied by whatever is the resistance. That is the way it is going to be. So I am going to really see a very, very large reduction in the eddy current loss. But of course, this is only per lamination. So I have to multiply this by, so this resistance has increased by a factor of 10, we said, right? So this will actually increase by a factor of 10. So this is 1 by 100 square multiplied by 10. So I'm going to have 1 by 1000. If there are 10 laminations, for every lamination, I'm going to have 1/1000th of the original loss. but I have to multiply this by the number of laminations themselves. I have to multiply this by the number of laminations. And the number of laminations now is 10. So this is going to become 1 by 100 times whatever was the original eddy current loss. So if I am going to have n laminations, I'm going to reduce the eddy current loss by 1 by n square factor when I am comparing this with the original eddy current loss that transformer was having with the solid core. So this is the total eddy current loss for all lamination. So that is the reason why normally no transformer with a ferromagnetic core will be made without laminating the core. You have to necessarily laminate the core. With the laminations only you will be making the entire core. So you would normally see that no 50 Hertz transformer or no high frequency transformer with a ferromagnetic core will be made with solid core at all. Never ever. So the eddy current losses are normally I square R losses that are happening, which means this is E square divided by R square multiplied by R. This is the kind of thing we are going to see. And E is proportional to frequency. Because E is proportional to frequency, you can say eddy current losses are proportional to frequency square. Eddy current losses are going to be proportional to frequency square, whereas hysteresis loss is going to be proportional to frequency. And both these components put together, we call them as core loss or iron loss, because this is due to the ferromagnetic core. So we call this as core loss or iron loss. And in a transformer, the flux which is causing the induction of EMF in the secondary side, that is essentially going to be a constant, because if there is a reduction in the flux because of the secondary current drawn, that is going to actually be replenished again by drawing an excess amount of primary current. So never will the flux in the core change. The core flux is going to almost remain as a constant as long as you apply rated voltage and rated frequency, because flux is proportional to whatever is the voltage divided by frequency. So phi m, we wrote E equal to 4.44 F phi m multiplied by the number of turns. So I can say if I am talking about a constant number of turns, I can say flux is proportional to E by F. So as long as I apply a constant value of voltage and constant frequency, if I say 220 volts 50 hertz transformer, I will always apply 220 volts and 50 hertz to this transformer no matter what. So the flux in a transformer is fairly a constant. So hysteresis loss, which is dependent upon the flux density, and similarly eddy current loss, which is also dependent upon the flux density square, they are going to be essentially changing as per the frequency at which you are operating the transformer. As long as the flux is kept as a constant, the frequency is going to decide really whether the eddy current losses are low or high, even if you laminate the core. The same way hysteresis loss will also be dependent upon the frequency. So one is dependent upon frequency square, the other one is dependent upon frequency itself. So if I know the total iron losses at different frequencies, I'd be able to segregate what is the value of eddy current loss and what is the value of hysteresis loss. I would be able to bifurcate those losses properly, provided I know the iron losses of the transformer at different values of frequencies. Okay. So eddy current loss is minimized in a transformer by laminating the core. When I laminate the core, I would be able to reduce eddy current losses. Whereas hysteresis losses are not going to be affected by lamination, but it is only affected by the property of the material of the core. Whatever is the material I'm using for the core, that is going to decide how much is the hysteresis loss. And what is the frequency of operation of this particular transformer supply? That is going to decide what is the hysteresis loss of the core. So we normally see that even under no load condition of the transformer, we would still have the losses due to the flux in the core. And that is essentially consisting of hysteresis loss, which is proportional to frequency, and his eddy current loss, which is proportional to frequency square. These are two components of iron losses. Okay. So in the next class, we will be looking at the loaded condition of the transformer. When I connect a load, so when a load is connected at the output, that is the secondary side of the transformer, then how does the transformer behave? This is what we are going to see in tomorrow's class. Okay.